Welcome to the last video for section C3 from Appendix C. In this section, we're going to talk about graphing trig functions. We're going to graph sine, cosine, and tangent. We're also going to graph the reciprocal trig functions, cosecant, secant, and cotangent. We don't do those very often, but it's nice to see the technique so that we know how to do those reciprocal trig functions when called upon. Now, the trig functions are functions like any other function. When you put a certain input in, you get a certain y value output. So if we knew the values of input that cause certain outputs, we should be able to create a table of points. And if we can create a table of points, we should be able to graph it. So I think we're going to start by creating a table of points for sine. So this is section C3. And we're graphing trig functions. Starting with the sine. Now, the table of values will be certainly an x and a y. But really, it's not x in this case because our input will be theta. And our y, it's not really going to be y necessarily, although it is an output, but we're going to get that y value from the sine of theta. And the thetas of interest, when you see an x, you know that's independent. Theta is independent as well. We can choose any angles we'd like. So I'm going to start with, how about minus 30 degrees? And then 0 degrees. And then 30, 45, 60, 90, how about 180, 270, and then let's finish off with 360. Full trip around the circle. While we're here, let's label these in radians. And double check as I go, because pi over 3 is 180 over 3 is 60. Pi over 2 is 180 over 2. That's 90. Pi is 180. And this is 3 pi over 2, and finally, full trip around the circle is 2 pi. Now, we should know the sign for these 5 common angles. The sine of 0 is 0. The sine of 30 degrees is a half. The sine of 45 is square root of 2 over 2. The sine of 60 is square root of 3 over 2. And the sine of 90, if you look at that table, is 1. Those values you can obtain from that handy reference table that I showed you in the other video, the big square root divided by 2. So you can either remember those, look them up on the table. The calculator can't give you the exact answer necessarily. There is another tool, and that's the unit circle. So let's refer to the unit circle for some of these other angles that we need. So let's go back and look at the unit circle, and let's go here to minus 30 degrees. Now, I don't see minus 30 degrees, but if I start here as the initial ray, my terminal ray is 30 degrees backwards. So minus 30 degrees would get me the same trig outputs as 330 degrees. Now, the sine of minus 30 should be the same as the sine of 330, which should be the y value. Remember, the sine is the y value on the unit circle. So the sine of minus 30 should be minus 1/2. Let's look at 180, 270, and 360 on a unit circle. We want sine, so I need the y value. So that would be 0, -1, 0. Now, what if we were to graph this collection of xy coordinates on a Cartesian plane? What would that look like? So first I'm going to establish the y-axis here, and then I'm going to establish the theta or x-axis here, the independent axis. So let's break this up. If we reach all the way out here to 2 pi, right in the middle should be pi. In the middle between 0 and pi should be pi over 2. And this third one right here, how do we get that? Well, that's actually the average of these two. So if you add those together, you get 3 pi. Average together means to divide by the number of entries, so divide by 2. 3 pi over 2. And if we go backwards by, let's see, well, we have to mark these off too. So let's do 45 degrees, which is right in the middle, pi over 4. And 30 and 60 should be about here and here. So here's pi over 6, and here's pi over 3. We kind of get those jammed in there. And then 30 degrees is minus pi over 6, minus 30 is right here. Now you notice that the sign peaks at 1, and it goes all the way down to minus 1, which should be down about here. And let's go ahead and label some of these coordinates, and let's see what the curve looks like. At 0 degrees, output 0. At pi over 6 or 30, the output is exactly 1/2. That's right there. At pi over 4, the output is square root of 2 over 2, which is about 0.707, which should be kind of right about there, I think. At 60 degrees, pi over 3, we're at square root of 3 over 2, which is 0.866, almost up to 0.9, actually. So that's about here. And finally, at 90 degrees, we've reached 1, which is right there. This is what the curve looks like so far. I'll sketch it in here. Now over here at 180 degrees, we're down to 0. Over here at 270 degrees, or 3 pi over 2, we're all the way down to -1. And way over here at 360 degrees, 2 pi, we're back to 0. And there is our sine curve, and by symmetry, we get a copy of this curve, and it comes down here. And then it shoots down into the negative y territory, and by symmetry again, it's going to look like that top curve, and then reach back here to the 0. Now, that is one cycle of the sine curve. Oh, don't forget, minus 30 is right here, and that's at -1/2, which is here. And if we go back to minus 90, by symmetry, we're probably down here. So this curve keeps going and going and going. It never stops. So it keeps going on that direction, and it's going to keep going on in that direction, up and down, up and down. That's your sine curve. Sine curve's important, very important. It's the light waves. It's what you're seeing right now. It's sound waves. It's what you're hearing. They're all sine curves. If you look at your electrical outlet, an alternating current outlet, it puts out a sine wave, 60 hertz sine wave. So there's no question that sine wave is important. Let's look at cosine as well. So cosine works a little differently. There's a slight shift to the cosine curve. In fact, the cosine curve likes to start at 1. And there are 5 key points. So let's just look at this one cycle over here. 2 pi all the way to the end of the circle, pi in the middle, and pi over 2 in between that. And if you want this middle point, you can average these two together, or oftentimes you can triple that one right there. It's the same thing. Now, because the cosine starts at 1, it has nowhere to go but down, and it's going to go all the way down to -1 over here. And now it has nowhere to go but up. So it goes up here and up to +1. Now, please don't draw a triangle wave. That is not a sine wave. Yes, you could connect the dots more or less and make a triangle here and here. But if you listen to the sound of a triangle wave, it's a very raspy sound. If you listen to the sound of a sine wave, it's a very pure tone, and that's a very natural sound. So don't draw a triangle wave. Let's draw a sine wave. Now, the best way to draw a sine wave is at these dots here. You can actually draw a little bit of a vertical line here and a little bit of a, horizontal line here and here. So the curve should be just about horizontal here and here, and even up here, just about horizontal. Now, rather than connecting the dot and shooting straight across, come out a little bit first. See? Come out. And then you can start curling down towards that point. Don't go directly for that point. Now, here, make it steeper. Don't shoot towards that point. Make it a little steeper, and then you can make the thing curl around and come around. It looks a lot better that way. Here, don't shoot across to that point. You want to come out a little bit, and then you can shoot across and make that point. Same thing here, don't connect the dots. Let's go a little steeper than that, and then you round it off at the top. That's a pretty good looking cosine curve. And don't forget the curve does continue on and on in both directions, just like that. If the sine and cosine curve didn't continue forever, we would never see starlight. You wouldn't be hearing my voice either. So it does go on and on in both directions, to positive infinity and negative infinity, both directions. Okay. Now, there's more to it than just the fundamental sine and cosine curve you're seeing right now. In fact, I want to measure two very important quantities on these curves, and then I'll talk about how to alter them a little bit. First thing I want to measure is amplitude. And amplitude is measured from the center of the curve, the x-axis in this case, up to the top, and it is always positive. In this case, the amplitude is 1. Same here. The amplitude is from the center of the curve to the top. So the amplitude is 1. The next thing to measure is the period. The period is the width of the repetition that you're seeing. And the period in this case is from 0 all the way to 2 pi. After that, it repeats itself. Same here. Period is from 0 all the way to 2 pi. After that, the curve repeats itself. So the natural period for the sine and cosine curve is 2 pi, but that's certainly not true of every sine and cosine curve. So let's take a look at altering the sine and cosine curve a little bit, in which we're able to modify that period and amplitude. So let's make y an output of our sine curve. And let's modify a few things. Let's make this 2, and let's make this the sine of, let's put a 2 in here as well. We'll refer to this as a coefficient A, and this can be coefficient B. Now, it turns out the amplitude is pretty easy. The amplitude, like the loudness on your stereo, and it really does represent loudness, by the way. The amplitude of an audio sine wave is the loudness. The amplitude of a light wave is the brightness. And the amplitude is always a positive measurement, so we want to make it positive with absolute value. In this case, it's 2. Now, you know the normal period of sine and cosine is 2 pi. And we want our periods to be positive as well. This little b can alter the period. And the way to compute period is 2 pi over b, but let's protect b with an absolute value in the rare case that that's negative. So instead of being the normal period of 2 pi, this particular sine curve operates between 0 and pi, and we get a full cycle. Let me show you how to graph this. So again, let's just graph one cycle. It's the 5 key points you want to look at. Now, what's the width of this curve going to be? Not 2 pi. Pi. And what do? We make 5 key points. We put one in the middle. Let's chop that in half. Let's put one in the middle here. Let's chop that in half again. And this third one is always the one that's more difficult to label. But I did tell you how to do it. You can either average these two together, or if your curve starts at 0, it'll always be triple that one. So it's going to be 3 pi over 4. Now the amplitude is 2. That's the loudness. That's how tall the curve is going to be. And so in this particular case, our curve is going to reach up to positive 2 and reach all the way down to negative 2. Now to graph it, all you need to know is how to graph the 5 key points for sine. Sine loves to start at the x-intercept, reach up to the maximum, go back down to the x-intercept, dip down to the minimum, and finish on the x-intercept. So let's start here at the x-intercept. Let's reach up for our maximum. Let's go back to our x-intercept on the 3rd key point, down to our minimum on the 4th key point, and then back to our x-intercept. And you'll notice that the sine curve itself hasn't changed very much. It's pretty much the same curve. What is different are the labels on our x and y axis. Remember to sketch those in. Don't make a triangle curve. Do your best to make it really look like a sine curve. And let's show that it does go on forever in both directions. Okay, so there is the way to graph a sine curve and the way to alter the amplitude and the period. Some other alterations that we can make, some transformations. We can take the sine and cosine curve and we can push them up in the y direction, pull them down in the y direction, and actually shift them to the left or to the right. We can do that too. So, to do that, what we're going to do is take a sine curve, maybe like this one, 4 sine of, how about theta over 2 maybe. This time I'm using theta as my independent axis. And I'm going to figure out that my amplitude is 4, and my period is 2 pi over absolute value of b. That's 2 pi over the absolute value of b, which is actually a half. That's 4 pi. That's much wider than an original sine curve. And let's do something else. Let's add 1 off the back end right here. Add 1 off the back end. So here's what that picture might look like. 1, 2, 3, 4, 1, 2, 3, 4. Now, I'm going to graph it without the plus 1 first. That would give me a period of 4 pi, chop in half, 2 pi, chop in half again. That's pi. And remember this one, the average of these two, or triple that one. And it's a sine curve, so it should go intercept, maximum, intercept, minimum, intercept. But I'm not going to really draw that because the plus 1 is a vertical transformation. So this is a rigid vertical transformation. And it's up by 1 unit. So let's take each of these points and shift them up 1 unit and put the real point there. Let's take each one of these and shift them up by 1 unit and put the real point there. Let's take this, shift it up 1 unit. Let's take this, shift it up 1 unit, and take this and shift it up 1 unit. So now I'll graph the actual sine curve that we're interested in, which is right here. So it's a sine curve. The amplitude is 4, but the whole thing got pushed up by 1 unit. And remember, it does go on forever and ever in both directions. So that is a method for graphing a sine curve with some transformations. One more thing to graph with a traditional trig function, and that would be tangent. For now, let's graph a tan bx. And if we want to set a equal to 1 and b equal to 1, we can start with that. Now, it turns out for tangent, the tangent of 0 is actually 0. The tangent of 90 degrees is the sine of 90 over the cosine of 90, but the sine of 90 is 1, and the cosine of 90 is 0, and that's not good. So the tangent of 90 is undefined. It's infinite, basically. And that's also true for the tangent of minus 90 degrees. We will also get undefined. So how do we represent the undefined portion of our tangent curve? It looks something like this. Well, the tangent of 0 is 0, so we can place a point right there. But over here at 90, or pi over 2, our tangent is getting so big that it's making its way to infinity. Over here at minus pi over 2, our tangent is getting so big that it needs a guide to infinity. Does anybody remember the tangent of 45 degrees? Pi over 4? Wasn't that just 1? And the tangent of minus 45, that's going to be minus 1 right here. Here's what the tangent looks like. It rides this asymptote up to infinity as it should. It goes through the 1 here and the 0 here and the negative 1, and then off it goes to negative infinity. What is the period of this curve? Take a good close look at it, and you realize that the period is pi. Pi over 2 here, pi over 2 here. What that means is that you're going to get repetition every pi units along the x-axis. Here's another one over here. So if this is pi over 2, let's add pi to that. That's 3 pi over 2. Let's add another pi to that. That's 5 pi over 2. And you should notice in the center point you'll get your 0, the center point you'll get your 0, and you're going to get this kind of repetition. You can even see that on your graphing calculator. Just repeat that over and over and over. So the period is pi. But we want to be able to alter these two coefficients. So the period is related to the b, but the normal period for tangent is not 2 pi, it's pi. So it's pi over b is the new period. Now a is not amplitude, because the amplitude is pretty much infinite for all of this. You can see there is no real amplitude, there's no limit to the y value. But what a does is alter this location here. Instead of 1 and minus 1, you're going to get a and minus a. So let's do one here. We're going to graph 3 tan of 2x. The period is pi over b. That's b. So pi over 2 is the period. So how do we do this? Now, between these two asymptotes, it's supposed to be pi over 2 wide. This whole thing is pi over 2 wide. And how do we make that happen? Well, you've got to divide this again in half. So this must be pi over 4, and this must be minus pi over 4. Add these two intervals up, you get your pi over 2. Now this key point in the middle here and here must be half of that. So pi over 4 divided by 2 again gets you pi over 8 and minus pi over 8. So these are my 5 key points. And what is that 3 going to do? Well, what it's going to do is 1, 2, 3. Where this key point used to go to 1 will now go to 3. 1, 2, 3. Same over here. This key point goes to negative 3 now. So this curve, and the 0 is still here, this curve is going to ride this asymptote down here, go through the 3, and then go through here. So it's not really supposed to be a line, it's a curve still, but it's gotten stretched quite a bit. It's gotten stretched quite a bit. Okay. And finally, let's talk about the reciprocal trig functions. I think I'm only going to get time to do one example. If I said that I would like you to graph y is equal, let's say 2 cosecant 4x. You can do this. And the way to do it is to do this. Your job is to graph the sine of 4x. Let's do that. So the job is to graph the sine of 4x. Well, circled here, the amplitude for the moment is still 1. Period is 2 pi over b, which is 4, which is pi over 2. It's a pretty narrow period. So we place our pi over 2 here. We chop in half. That's pi over 4. We chop in half. That's pi over 8. Remember, this middle one here is always 3 of these, or average those two. So that must be 3 pi over 8. And you know what? The amplitude's 1. So I'm going to put my 1 here, and I'll put my negative 1 here. So I'm going to just sketch in this sine curve ever so lightly, because I don't really want this sine curve. I want the cosecant. So let's see how that would be done. So I'm sketching in that little sine curve that has period 2 pi and amplitude 1. Now hang on a second. I don't really want the sine. I want 1 over the sine. So you see this where it says 0 over here, y equals 0? I don't want sine, which is 0. I want 1 over 0. Well, we all know what 1 over 0. 1 over 0 is undefined. And undefined requires an asymptote. Here's another 0. That's the sine, though. I want 1 over that. Well, 1 over 0 is infinity, and I need a guide. Same here. Here's another 0. But I want 1 over that. 1 over 0 is infinity. Now, how about over here at 1? I don't really want 1. I want 1 over 1. Oh, so I do want 1, but then times 2. So that would go here on the actual curve right there, 2. Do you see what I did? I took the y value, I did 1 over the y value, 1, and then 2 times that is 2. How about down here where we're getting 1/2? Well, I don't want 1/2. I want 1 over 1/2, which is 2, but then 2 times 2, way up here is 4. So this point gets transformed to 4. Here's another 1/2 that gets transformed up to 4. And now you can see part of the cosecant curve right here. Almost looks like a little parabola sitting up here. And of course, it's riding those asymptotes up to infinity. Well, the same is going to work down here. So here's 2, and let's say here's 4. So -2, -4. So same situation here. Here is a -1. 1 over -1 is -1, but that 2 times gets you -2. Here's -1/2 here and here. The reciprocal of -1/2 is -2, but don't forget there's a 2 out there to double it up to get -4 here and also here. So here's another aspect of the cosecant curve. They kind of look like 2 parabolas, but they're not really parabolas because they ride asymptotes up to infinity, and parabolas don't do that. Parabolas will extend in the x direction, both in the positive and negative. Well, I hope that's helped you. This has been a little bit of a lengthy video. I apologize, but I did want to cover all the aspects of graphing. And really, again, the best way to work on this is to do the homework. You'll get the best experience that way. So thanks for your time and attention. And I will see you in class. And that finishes off this first week and Appendix C. So on to bigger and better things. We're going to look at some more pre-calculus and a preview of calculus, and then finally we're going to get to do some calculus. Thanks, everyone.